In this video, let us derive Mayer's relation. Julius von Mayer was a German physicist who has contributed greatly to the field of thermodynamics. He tried to connect the specific heat capacity of a gas at constant pressure and at constant volume. Now, let us derive his relation Cp minus Cv equal to R. For this, let us take a polished non-conducting cylinder as shown in this figure, and this cylinder is provided with a smooth non-conducting piston which can be lifted up and down. Now, let us fill this cylinder with m kg of gas, and the area of cross section of this cylinder is A. The initial conditions of the gas like pressure, volume and temperature are noted as capital V, P, capital V and T respectively. Now let us provide some heat energy to this gas. Generally, when we provide heat energy to any substance, its temperature rises. Now let us provide some certain quantity of heat to the gas so that the temperature of the gas increases by dt. We can provide heat energy to or supply heat energy to the gas at two different situations. One by keeping the pressure of the gas constant and by keeping the volume of the gas constant. First, let us supply some heat energy by keeping the volume of the gas constant. So, to keep the volume of the gas constant, the piston is kept down as we have kept at the initial condition. So, the heat provided to the gas is computed as, or it is given by m into Cv times into dt. Generally, the heat provided to any substance is measured as mass of the substance multiplied by the specific heat capacity into the rising temperature. So, here the mass of the gas is m, the specific heat capacity is measured at constant volume, so it is Cv, and the rising temperature is dt. So, the quantity of heat given to the gas is m times Cv times dt. So, all these heat energy supplied to the gas is completely used in increasing the internal energy of the gas. That means for rising the temperature of the gas at constant volume. So, increase in the internal energy of the gas is equal to m into Cv times dt. Now, let us look at the second case. So, in the previous case, if you keep the volume constant, the pressure may vary. It may increase or decrease. So, here to keep the pressure constant, the volume should be adjusted because they are inversely proportional to each other. So, now we are providing the same quantity of heat to the same mass of the gas to raise the temperature by the same amount dt at constant pressure, or that means the pressure of the gas should be maintained constant. So, to maintain the constant pressure, the the piston is lifted up by a certain distance. So, the volume changes. So, the change in the volume is noted as dV, and the distance through which the piston moved is noted as dx. So, the quantity of heat supplied to the gas in this case is m into Cp times dt. So, the mass into the specific heat capacity of the gas at constant pressure multiplied by the rise in temperature dt. But in this case, the heat provided to the gas is utilized for two reasons. One is for rising the internal energy of the gas corresponding to the temperature dt, for the rising the temperature dt, and the second part, another part of the gas is used for pushing the pistons, that means for expanding the gas to keep the pressure constant. So the heat provided mcp dt is used for increase in the internal energy plus the external work done, that is for pushing the piston. So we have already noted the increase in internal energy is equal to m times cv times dt. So next let us calculate what is the amount of work or the external work done for raising the piston. We generally know the work is given by force into distance. Here we do not have the direct value for the force, but we know the pressure is equal to force per unit area, that is F by A. So from this let us find out what is force. Force is equal to pressure into area. So let us substitute it, pressure into area, and the distance through which the pistons moved is dx. So P into A into dx. We all know the area is not area into the distance, that is the thickness dx is nothing but it is the dv, the change in the volume. So the external work done dw is equal to pdv. So we can write mcp dt is equal to mcv dt plus the external work done pdv. We all know for a perfect gas, the perfect gas equation is pv equal to m times RT, and we are the small r is nothing but it is a gas constant per unit mass. Let us differentiate this gas equation, perfect gas equation. So P is also a variable, V is also variable. Let us make use of D of UV formula. So it is UdV plus VdU. So PdV plus VdP. So in first case you will keep P constant and differentiate V. So it is P into dV plus the second term will have V constant and differentiating dP is equal to m is a constant, the mass of the gas is constant, r is a constant, the only factor that varies is temperature, so it is dt. Since in this the pressure is kept constant, the dP will be equal to 0. We all know when we differentiate a constant we end up at 0. So substituting there we get pdV equal to mr dt. So in place of pdV let us write mr dt. Throughout this equation m is there, let us m is also there, dt is also there, let us divide it by m dt. When we divide we get Cp equal to Cv plus R, or we can write Cp minus Cv equal to small r. This Cp and Cv are if replaced by a molar specific heat capacities at constant pressure and constant volume, then we can replace R small r by capital R, that is for larger quantities. So we can say Cp minus Cv equal to capital R, which is the most celebrated Mayer's relation which connects the specific heat capacity of a gas at constant pressure and at constant volume. That means the specific heat capacity of a gas at constant pressure exceeds the specific heat capacity of a gas at constant volume by R amounts.